And HVAC full practice exam number 1, problem 74. There are several refrigeration questions that always give a capacity in BTU per hours or tons. Does that always apply to the evaporator? Are there any cases where that would apply to the condenser? See the attached example problem. So this example problem was a refrigeration cycle with a cooling capacity given in tons. And this other example was a heat pump operating in cooling mode where the capacity is given in refrigeration tons. So the answer is, if it's given in tons, yes, it always refers to the evaporator because the problem is about refrigeration or air conditioning or a heat pump that's being operated in cooling mode. So it's about a refrigeration cycle in all those cases. If it's a heat pump being operated in heating mode, then we would not refer to the capacity in tons. We would have to say BTUs per hour in that case. And it's also worth reminding that the capacity of the heat pump operating in heating mode is going to be not only stated in different units, that's to be BTU per hour instead of tons. And by the way, the cooling capacity could be stated in BTU per hour or tons, but just the fact that it's stated in tons makes it very clear that it's about refrigeration. And I think that's clear in this problem too. It's a refrigeration cycle with a cooling capacity, and this one is a heat pump operated in cooling mode. So if I just said there's a heat pump, it would be ambiguous. But then if I said it's a heat pump with a capacity of 2 refrigeration tons, then actually it's redundant to say it's operating in cooling mode because it would have to be in cooling mode. Unless I was trying to trick you and it was given the capacity of the heat pump in cooling mode when I actually wanted you to analyze how it was being run as a heater. But that's a little nasty if they do that on the exam. So while we're on the topic, I think it's a good opportunity to remind the difference between the COP for a refrigerator and a heat pump and how they're related. So as you'll recall, the COP for a heat pump, well, let's say this. What is the COP? COP is the output over the input, right? It's the bang for the buck, and they have to be in the same units. So for a heat pump, you would say there's some heating capacity, which is sometimes you'll see this written as QH, but to be even more precise about it, that's the condenser, isn't it? Because we're trying to reject heat from the condenser in a useful way if our goal is to do heating. And what do we pay? What's the input in order for us to do that heating? That's the work of the compressor. So this expression represents the COP of a heat pump. And that's equal to the COP of a refrigerator, the same heat pump operated in cooling mode, which is Q evap. It's the cooling that's provided by the evaporator. Well, I presented this in a funny way. I have to go through with it now, but it would have been more impressive if I hadn't written this all out first. What I wanted to do is say this. In general, for a refrigeration cycle, the heat out of the condenser is equal to the heat into the evaporator plus the work done by the compressor, which also turns into heat. And then you can divide all three of those expressions by the same number because algebra allows that. And then this term becomes 1. And this is the COP of a heat pump, and this is the COP of a refrigerator. So the COP of a heat pump equals the COP of the same heat pump operated in cooling mode as a refrigerator plus 1. So you always get a little bit more bang for your buck when you run the heat pump as a heater because the work of the compressor turns into heat. And if your goal is to heat, then that heat is useful. But if your goal is to cool, that's more heat that you then have to remove. So it becomes an uphill battle. Refrigeration is always a little bit harder. But the typical temperature ranges with which you would operate an air conditioner is usually something like 90 to 100 degrees outside. Maybe you're somewhere where it's really hot and it's like 110, and you're trying to get the space down to 75. So that's a delta T of maybe 25 to 35. But in a heating application, if you want to get your space to 70 and it's 20 degrees out or 10 degrees out or 0 degrees out, you have really, really big delta T's to overcome. So that can also affect the efficiency and unexpected ways. So a few things to think about there. Some just kind of wanted to remind you of the fundamental theory, kind of connecting these ideas, but also keeping in mind how that actually plays out in applications. Probably a tangent from what this question was really asking, but couldn't help myself.